Have you ever looked up at the night sky, mesmerized by the vast tapestry of stars, and wondered how those majestic galaxies came to be? The swirling arms of spiral galaxies, the glowing cores of elliptical ones. These cosmic wonders didn't just appear overnight. They're the result of an epic journey spanning billions of years, a story written in the language of gravity, gas, and time. Picture this: trillions of tons of scattered hydrogen, drifting through the darkness like fog, slowly pulled together by forces we're only beginning to understand. From those chaotic beginnings, galaxies emerge, evolving into the breathtaking structures we see today. But how does something as delicate as a gas cloud transform into a sprawling galactic masterpiece, complete with spiral arms, blazing stars, and mysterious dark matter? That's the story we're about to unravel. Think about the scale for a moment. A single galaxy can contain hundreds of billions of stars, each with its own planets, asteroids, and possibilities. And yet, every one of those galaxies started as nothing more than a faint whisper in the cosmos, a cloud of gas so diffuse, it's hard to believe it could become anything at all. But within that gas lies the secret to everything. Gravity tugs at those particles, drawing them closer, heating them up until the first stars ignite like candles in the dark. Over eons, those stars live, die, and explode, scattering heavier elements back into the void, seeding the next generation of stars and planets. It's a cycle as old as the universe itself, and it's happening right now in galaxies far beyond our own. What's even more astonishing is that we're part of this story too. The atoms in your body, the iron in your blood, the calcium in your bones, they were forged in the hearts of stars that lived and died long before our solar system existed. We're not just observers of this cosmic drama, we're products of it. So when we trace the evolution of galaxies, we're also uncovering our own origins. Over the course of this video, we'll follow the incredible journey from those primordial gas clouds to the intricate spiral arms we admire today. We'll explore the forces that shape galaxies, the mysteries that still puzzle astronomers, and the breathtaking discoveries that remind us just how dynamic and alive our universe really is. This isn't just a story about distant stars, it's a story about us and our place in the grand tapestry of existence. So let's dive in. To understand how galaxies begin, we need to rewind the clock, way back to a time when the universe was nothing but a dark, swirling sea of gas. In those early moments after the Big Bang, hydrogen and helium were the only elements in existence, drifting through space like an invisible fog. But this wasn't just any fog, it was the raw material of everything to come. Picture vast clouds stretching hundreds of thousands of light years across, so thin that a single cubic meter might hold only a handful of atoms. Yet within those sparse clouds, gravity was already at work, pulling particles together in a slow, cosmic dance. But gravity alone couldn't have built the galaxies we see today. There was another invisible player shaping the universe: dark matter. Though we can't see it or touch it, dark matter's gravitational pull is what created the framework for galaxies to form. Think of it like scaffolding around a building, unseen but essential. As dark matter clumped together, it created deep gravitational wells, pulling in the surrounding gas like water swirling down a drain. Over millions of years, these pockets of gas grew denser and hotter until the first stars ignited within them, scattering light into the darkness for the very first time. What's fascinating is how chaotic this process was. Those early gas clouds didn't collapse neatly. They swirled, collided, and fragmented, creating a turbulent birthplace for galaxies. Some regions became dense enough to form stars almost immediately, while others took much longer, leaving behind vast stretches of gas that would eventually become spiral arms or glowing halos. And all the while, dark matter's invisible hand kept guiding the structure, shaping the destiny of these cosmic nurseries. This wasn't a quick process. It took hundreds of millions of years for those first protogalaxies to take shape, growing larger as they pulled in more gas and merged with their neighbors. The universe was still young, but already the seeds of today's grand spirals and colossal ellipticals were being sown. And when we look at distant galaxies through our telescopes, we're actually seeing snapshots of this ancient era, light that's traveled billions of years to reach us. So in a way, studying galaxy formation isn't just about the past, it's about watching the universe grow up in real time. Dark matter doesn't just nudge galaxies into existence, it orchestrates their entire design. While we can't see it, its gravitational fingerprints are etched into the cosmos, dictating where stars form, how galaxies cluster, and even the speed at which they spin. Picture a marionette strings, unseen yet controlling every movement. That's dark matter's role in the universe. Without it, galaxies as we know them wouldn't exist. Their spiral arms would unravel, their stars would scatter, and the cosmic web connecting them would collapse into chaos. How do we know dark matter is real if we can't detect it directly? The evidence is written in the motion of galaxies themselves. Take the Andromeda Galaxy, our closest neighbor. Stars on its outer edges whirl around the center at speeds that defy the laws of gravity, unless there's an enormous halo of invisible mass holding them in place. Visible matter alone can't account for this motion. It's like watching a merry-go-round spin impossibly fast, then realizing there's a hidden engine beneath it. That's dark matter, the unseen force keeping everything from flying apart. But dark matter's influence goes far beyond individual galaxies. It sculpts the universe's large-scale structure, weaving vast filaments that connect galaxy clusters like threads in a spiderweb. These filaments, composed mostly of dark matter, act as cosmic highways, guiding galaxies into clusters and superclusters over billions of years. Simulations of the universe, run with and without dark matter, reveal just how critical it is. Without it, galaxies remain scattered and sparse. With it, they assemble into the intricate, clustered patterns we observe today, yet mysteries remain. Scientists still debate what dark matter actually is. Some theories suggest it's made of weakly interacting massive particles, or WIMP, that barely interact with normal matter except through gravity. Others propose actions, hypothetical particles lighter than electrons. Then there's the possibility that our understanding of gravity itself is incomplete, an idea that challenges Einstein's theories. Whatever the answer, one thing is clear: dark matter isn't just a minor player in galaxy formation. It's the foundation, the blueprint, the invisible hand shaping the universe from the shadows. And here's the most tantalizing part: every galaxy we see is just the tip of the iceberg. For every glowing spiral or elliptical, there's up to 5 times more dark matter hidden in its halo, stretching far beyond the visible stars. This means most of the universe's mass is missing from our telescopes, detectable only by its gravitational whisper. It's a humbling reminder that what we see is only a fraction of what's out there, and that the true architects of the cosmos are still waiting to be discovered. Those vast interstellar gas clouds may look empty, but they're cosmic gold mines packed with the ingredients for entire galaxies. Mostly hydrogen with some helium and traces of heavier elements, these clouds are staggeringly sparse by Earth standards. A typical cloud might contain just 100 atoms per cubic centimeter, making it a better vacuum than anything we could create in labs. Yet across light years of space, that adds up to enough material to birth millions of stars. The magic happens when gravity overcomes the cloud's internal pressure, triggering a collapse that transforms diffuse gas into dense stellar nurseries. Temperature plays a surprising role in this stellar alchemy. Warmer clouds resist collapse, their particles moving too fast to clump together easily, while colder regions become gravitational hotspots. Some of the most productive star-forming clouds hover just 10 degrees above absolute zero. But there's a twist: as gas collapses, friction heats it up, which could stop the process prematurely. That's where cosmic dust comes in. tiny solid particles, mostly silicates and carbon compounds, act like radiators, absorbing heat and re-emitting it as infrared light, allowing the cloud to keep contracting. Turbulence adds another layer of complexity. These aren't serene pools of gas but churning, chaotic systems with supersonic internal winds. Like whirlpools in a river, turbulent eddies create dense knots where gravity can gain a stronger foothold. Astronomers compare it to a bubbling pot of water, regions constantly rising, falling, and colliding. Without this turbulence, gas might collapse too quickly into a few massive stars instead of the diverse populations we observe. The Milky Way's Orion Nebula shows this beautifully, with its filamentary structures and varied stellar densities revealing the interplay between turbulence and gravity. Perhaps most astonishing is how these clouds remember their past. When massive stars die in supernova, they seed the surrounding gas with heavy elements like oxygen, carbon, and iron. Future generations of stars and their planets inherit this enriched material. Our own solar system formed from such recycled debris, meaning the iron in your blood and the calcium in your bones were forged in ancient stellar explosions. These clouds aren't just birthplaces, they're cosmic recycling centers, constantly repurposing material across billions of years. The scale of these processes defies imagination. A single star-forming cloud like the Taurus molecular complex spans over 100 light-years, yet appears nearly invisible until its hidden stellar nurseries begin glowing. Infrared telescopes reveal these secret construction zones, showing glowing knots where protostars are taking shape, each potentially destined to become the heart of a planetary system. And everywhere we look, from our galactic neighborhood to the most distant observable galaxies, the same basic recipe repeats. Gas plus gravity plus time equals the grand structures lighting up our universe. Gravity works its magic silently, patiently, pulling together atoms that might otherwise drift apart forever. But there's a tipping point, a moment when a gas cloud can no longer resist its own weight. This is where Jeans instability comes into play, a cosmic rulebook for collapse. Named after physicist James Jeans, it tells us when a cloud's gravity overpowers its internal pressure, triggering a cascade of fragmentation. Imagine a balloon filled with smoke. If you squeeze it gently, the smoke resists, but apply enough pressure and it suddenly buckles into dense pockets. That's Jeans instability in action, gravity's victory over outward pressure. The math behind it is elegant. A cloud's fate hinges on its mass, temperature, and density. Cooler, denser clouds are more likely to collapse because their atoms move sluggishly, offering less resistance to gravity's pull. But here's the catch: as the cloud shrinks, it doesn't collapse uniformly. Instead, it splinters into smaller, denser clumps, each destined to become a star or part of a star system. This fragmentation explains why galaxies don't form single, monolithic stars, but instead produce dazzling stellar families of all sizes. What's mesmerizing is how chaotic yet precise this process is. Turbulence within the cloud creates swirling eddies, while magnetic fields threading through the gas like invisible wires add another layer of complexity. These fields can slow collapse in some regions, creating filamentary structures where stars eventually line up like pearls on a string. The famous Orion Nebula offers a front-row seat to this phenomenon, with its glowing tendrils of gas lit up by newborn stars. But gravity doesn't work alone. As dense cores form, they begin to rotate, spinning faster as they shrink, a cosmic version of a figure skater pulling in their arms. This rotation flattens the collapsing gas into disks, which later feed growing stars and, in many cases, become the birthplaces of planets. Some of these disks might even give rise to spiral arms, weaving the grand designs we see in mature galaxies. And then there's the feedback loop. The first massive stars to ignite within these collapsing clouds don't just shine, they reshape their surroundings. Their fierce radiation and stellar winds blow away nearby gas, halting star formation in some areas while compressing it in others. It's a self-regulating process, ensuring galaxies don't burn through their fuel too quickly. This delicate balance between creation and destruction is what allows galaxies to evolve over billions of years, transforming primordial chaos into the structured beauty we see today. Yet even now, astronomers are uncovering new twists. Some clouds collapse faster than expected, while others defy predictions entirely. Computer simulations reveal intricate dances of gas and gravity, but they also highlight gaps in our understanding. Every observation, from nearby stellar nurseries to the most distant protogalaxies, adds another piece to the puzzle. And with each discovery, we're reminded that the universe's recipe for galaxy formation is far more nuanced and more astonishing than we ever imagined. The universe's first galaxies didn't emerge fully formed. They began as messy, turbulent prototypes known as protogalaxies. These cosmic infants bore little resemblance to the sleek spirals or smooth ellipticals we see today. Instead, they were chaotic, lopsided collections of gas and stars, more like splatters of paint on a dark canvas than the refined masterpieces of modern galaxies. Picture a construction site in its earliest phase. No blueprints, just raw materials heaped together, with gravity scrambling to impose order on the chaos. What made protogalaxies so different? For starters, they lacked the clear structure of today's galaxies. Without well-defined spiral arms or symmetrical bulges, they were more like bloated, glowing blobs. Their stars formed in frenzied bursts, ignited by collapsing pockets of gas that hadn't yet settled into stable orbits. And because the early universe was smaller and denser, these protogalaxies were crowded close together, constantly bumping into one another like bumper cars, merging and reshaping in a cosmic game of survival. One of the most striking differences was their composition. Modern galaxies are recycled, enriched by generations of stars that lived, died, and spewed heavy elements back into space. But protogalaxies were pristine, made almost entirely of hydrogen and helium, the only elements forged in the Big Bang. Their stars, known as population 3 stars, were massive, hot, and fleeting, burning bright and dying young in spectacular supernovae. These explosions seeded the surrounding gas with the first heavier elements, setting the stage for future, more diverse generations of stars. Yet despite their chaos, protogalaxies held the seeds of order. Dark matter halos, invisible but relentless, provided the scaffolding for structure to emerge. Over hundreds of millions of years, gravity smoothed out the irregularities, drawing gas into rotating disks and funneling stars into more organized orbits. Mergers played a crucial role. Two smaller protogalaxies collided and combined, their mutual gravity sculpting them into larger, more stable systems. The Hubble Space Telescope has given us glimpses of these ancient building blocks. In deep field images, the faintest, reddest smudges represent protogalaxies as they appeared over 13 billion years ago. Some are no bigger than 1/10 of the Milky Way, yet they're teeming with star formation, blazing with the energy of youth. And because light takes time to reach us, these snapshots allow us to watch the universe's awkward phase before galaxies grew into the elegant structures we know today. What's astonishing is how much diversity existed even then. Some protogalaxies were gas-rich, birthing stars at breakneck speeds, while others were quieter, their growth stunted by feedback from early supernova or the harsh radiation of nearby quasars. This variation hints at why modern galaxies come in so many shapes and sizes. Their earliest beginnings already carried the fingerprints of their future forms. And here's the mind-bending part. Some of these protogalaxies might still exist. Ultra-faint dwarf galaxies orbiting the Milky Way, like Segway 1 or Draco 2, could be cosmic relics, primordial fragments that never merged into larger systems. Studying them is like finding living fossils, offering clues about the universe's first steps toward structure. They remind us that galaxies aren't static. They're ever-evolving, their stories written across billions of years, from the first flickers of starlight to the grand designs we admire today. When gravity finally wins its battle against pressure inside those collapsing gas clouds, something extraordinary happens. The universe lights up for the first time. Deep within these dense pockets of hydrogen and helium, temperatures soar to millions of degrees, atoms smash together with such force that they fuse, and a star flickers to life. These weren't just any stars, though. The very first generation, known as Population 3 stars, were unlike anything we see today. Imagine behemoths 100 times more massive than our Sun, blazing with blue-white intensity, their nuclear furnaces running at full throttle. But their brilliance came at a cost. They burned fast and died young, their lifetimes measured in mere millions of years rather than billions. What made these stars so special wasn't just their size, it was their chemistry. Born from pristine gas untouched by previous generations, they contained nothing but hydrogen and helium, the raw elements forged in the Big Bang. Yet within their cores they cooked up something new, heavier elements like carbon, oxygen, and even traces of iron. When these short-lived giants finally exploded as supernova, they didn't just vanish, they scattered these newly minted atoms across space like cosmic confetti. This was the universe's first act of recycling, seeding the gas clouds around them with the building blocks for future stars, planets, and even life itself. But these supernovae did more than just spread elements, they reshaped their surroundings entirely. The shock waves from their explosions compressed nearby gas, triggering new rounds of star formation in a self-perpetuating cycle. Picture a row of dominoes falling, each collapse setting off the next. Regions that had been quiet for eons suddenly burst into activity, with clusters of stars igniting in rapid succession. This is how galaxies began to grow, not as solitary stars, but as sprawling families, their members bound together by gravity and shared history. The legacy of Population 3 stars lives on in us. Every atom of oxygen we breathe, every particle of calcium in our bones, was forged in stars like these, either in their violent deaths or in the generations that followed. It's humbling to think that the materials making up our world were once stardust, scattered across the cosmos by explosions that occurred before Earth even existed. And while we've never directly observed a Population 3 star, they vanished long ago. Their fingerprints are everywhere. The oldest stars we've found, like those in the Milky Way's halo, contain barely a sprinkle of heavier elements, telling us they formed from gas touched by just a few of those primordial giants. Yet mysteries remain. How exactly did these first stars form in such perfect isolation? Why did they grow so massive compared to modern stars? Simulations suggest their birth clouds lacked the dust and heavy elements that help today's gas clouds fragment into smaller stars, leaving gravity free to amass enormous stellar giants. But without direct observations, we're piecing together their story from clues left behind like detectives, reconstructing a crime scene from scattered evidence. What's clear is that these stars didn't just light up the cosmos, they transformed it. Their deaths marked the end of the universe's dark ages and the beginning of its chemical evolution. With each generation of stars, galaxies grew richer, more complex, and more capable of fostering planets and perhaps life. So the next time you look up at the night sky, remember, those twinkling lights aren't just distant suns. They're part of an unbroken chain stretching back to the very first stars, whose explosions wrote the recipe for everything that followed. Those first massive stars didn't just shine. They roared into existence with enough power to reshape entire galaxies. Their stellar winds blasted outward at millions of kilometers per hour, carving vast bubbles in the surrounding gas like a cosmic blowtorch melting wax. These weren't gentle breezes but supersonic tsunamis of charged particles, powerful enough to sweep up interstellar material and push it into dense shells at their edges. Within these shells, something remarkable happened. The compressed gas reached critical density, triggering new rounds of star formation in perfect rings around the parent star. It's a galactic domino effect. One massive star's winds create the conditions for dozens more to form nearby, like fireworks setting off neighboring fuses. And when these stellar titans reached the end of their brief lives, their final act dwarfed even their spectacular winds. Supernova detonated with the energy of 100 billion suns, briefly outshining entire galaxies. The shockwaves from these explosions traveled hundreds of light years, leaving behind intricate filaments of glowing gas and injecting space with newly forged elements. Gold, uranium, even the iodine in your thyroid, all were created in these cataclysmic moments and hurled into the void. But these explosions weren't just destructive, they were creative forces. Like a blacksmith's hammer shaping molten metal, supernova shockwaves molded the interstellar medium, creating pockets of turbulence where future stars would one day coalesce. This feedback loop, stars forming, living, and dying, became the universe's self-regulating system. When star formation ran too hot, supernova blasted away nearby gas, putting the brakes on further stellar births. When things grew too quiet, compressed shockwave fronts collapsed into new stellar nurseries. Even today, we see this balancing act play out in places like the Carina Nebula, where newborn stars wage war against their own birth clouds, their radiation eroding the very material that created them. It's a dance as old as time itself, creation arising from destruction, order emerging from chaos. The most fascinating part, we're seeing this process unfold differently across the cosmos. In dwarf galaxies like the Small Magellanic Cloud, supernova can actually strip away most of the gas entirely, leaving behind stunted stellar populations. Meanwhile, in dense galactic cores, supernova explosions pile material onto growing supermassive black holes, fueling quasars that outshine entire galaxies. Each environment writes its own variation on this universal theme, proving that while the ingredients may be the same, the recipes vary wildly across the universe. Perhaps most astonishing is how these ancient processes still shape galaxies today. When astronomers examine the chemical makeup of stars in the Milky Way's outer halo, they find distinct layers like tree rings, recording periods of intense supernova activity billions of years ago. Our galaxy carries these scars from its violent youth, a reminder that the delicate spiral we see today was forged in countless stellar explosions. And somewhere out there, new supernova are preparing the groundwork for galaxies not yet born, continuing the cycle that began when the first stars illuminated the darkness. Galaxies don't grow in isolation, they collide, merge, and reshape one another in a cosmic ballet that unfolds over billions of years. Imagine two vast islands of stars, each with its own structure and rhythm, slowly drifting toward each other until gravity takes over, twisting their shapes into something entirely new. This isn't destruction, it's transformation. Galactic mergers are the universe's way of building giants from fragments, turning small, chaotic protogalaxies into the majestic spirals and ellipticals we recognize today. One of the most spectacular examples happening right now is the eventual collision between our Milky Way and the Andromeda Galaxy. Currently hurtling toward each other at over 100 kilometers per second, these two spirals will meet in about 4 billion years. But don't picture a violent crash, it's more like a slow-motion tango. Stars are so far apart that they'll mostly glide past one another, their paths bending under gravity's pull until the galaxies become inseparable. The result, a massive elliptical galaxy, its stars no longer arranged in delicate spirals but orbiting in a glowing, football-shaped haze. Smaller mergers leave their own signatures. Take the Tadpole Galaxy, its long tail of stars stretching over 200,000 light-years, a smoking gun of a recent collision. When galaxies merge, tidal forces rip streams of stars and gas from their outskirts, creating these spectacular trails. The Antennae galaxies show an even earlier stage, their two cores still distinct but already wrapped in luminous tendrils of newborn stars, ignited as colliding gas clouds compressed and burst into flame. These mergers aren't just about size, they're star-forming fireworks, triggering starbursts so intense they can outshine the rest of the galaxy combined. But mergers don't just add stars, they rewrite galactic DNA. When galaxies combine, their stars get shuffled into new orbits, some flung outward into halos, others sinking toward the core. The Milky Way's own halo contains ancient stellar streams like Gaia Enceladus, the remnants of a dwarf galaxy devoured 10 billion years ago. Even our solar system might owe its existence to a long-ago merger that stirred up gas clouds and sparked a wave of star formation. The strangest mergers reshape galaxies in ways we're still deciphering. When a small, gas-rich galaxy plunges into a larger one at the right angle, it can funnel gas straight to the core, igniting quasars or feeding supermassive black holes. Other mergers leave behind shell galaxies, where concentric ripples of stars like frozen waves testify to a violent past. And sometimes galaxies pass through each other like ghosts, their stars unaffected but their gas clouds colliding so violently they light up in a brief but brilliant burst of blue. What's astonishing is how common this process is. Peer deep enough into space, and nearly every galaxy shows signs of past mergers, tidal tails, distorted shapes, or unexpected clusters of stars. Even pristine spirals like the Pinwheel Galaxy likely grew by absorbing smaller neighbors, their delicate arms hiding a history of cosmic cannibalism. The universe is a dynamic place where galaxies are never truly finished, always evolving through collisions that build, destroy, and rebuild them over eons. And here's the twist: mergers might be the key to understanding why galaxies look so different today. Ellipticals, with their old, red stars and random orbits, are often the products of major mergers that exhausted their gas. Spirals, rich in star-forming material, might have avoided catastrophic collisions so far. Even dark matter plays a role, its invisible halos determining whether galaxies merge smoothly or rip each other apart. Every galactic shape tells a story of encounters past, a record of violence and rebirth written in starlight. So the next time you see a galaxy, remember, it's not just an island of stars. It's a living archive, its structure a mosaic of mergers stretching back to the dawn of time. And somewhere out there, new collisions are already underway, shaping the galaxies of tomorrow in a cycle as old as the universe itself. The universe doesn't build galaxies on a single blueprint, it crafts them in two strikingly different flavors: the elegant spirals with their swirling arms, and the smooth, featureless ellipticals resembling glowing footballs. What determines which path a galaxy takes? It all comes down to two critical factors: their merger history and how much gas they've managed to hold onto over billions of years. Spiral galaxies, like our Milky Way, are the cosmic equivalent of well-oiled machines, flat, rotating disks where gas-rich arms churn out new stars at a steady pace. Their secret lies in a relatively quiet life. When spiral galaxies do merge, it's often with smaller companions, gentle encounters that don't completely disrupt their delicate structure. These mergers add fresh gas to the system, fueling ongoing star formation and maintaining those iconic spiral patterns. The disk shape persists because the gas has time to settle into an orderly rotation, cooling and flattening like pizza dough spun in the air. Elliptical galaxies tell a far more dramatic story. These galaxies are the cosmic equivalent of battered warriors, their stars orbiting in chaotic, random directions with no clear disk or spiral structure. This disarray is the result of violent, head-on collisions between massive galaxies of similar size. When two spirals collide, their gas clouds smash together in a frenzy, triggering bursts of star formation so intense they can exhaust all available fuel in just a few 100 million years. Without gas to form new stars, the galaxy's stellar population ages uniformly, leaving behind the reddish glow of old stars. The random orbits come from the merger's gravitational chaos, like mixing two pots of marbles by shaking them violently. the stars lose their original trajectories and settle into a hazy, three-dimensional cloud. Gas content plays an equally crucial role. Spiral galaxies are cosmic reservoirs, constantly replenishing their gas supplies from intergalactic filaments or careful mergers. This fresh hydrogen keeps their star-forming factories running, painting their arms with young blue stars and glowing nebulae. Ellipticals, by contrast, are cosmic deserts, their gas either burned up in post-merger starbursts or stripped away by the searing heat of their own supermassive black holes, which blast out radiation when activated during collisions. You can think of spirals as lush rainforests, continually renewing themselves, while ellipticals are ancient orchards where every tree was planted in one frantic season long ago. Even the dark matter halos surrounding these galaxies differ. Spirals tend to live in quieter cosmic neighborhoods, their halos relatively undisturbed. Ellipticals often sit at the crowded hearts of galaxy clusters, where frequent gravitational encounters keep them gas-poor and puffed up. It's like comparing a solitary tree growing in open space free to spread its branches evenly, to one in a dense forest forced into a narrower shape by its neighbors. Yet exceptions exist, proving the universe loves variety. Some spirals, like NGC 4548, show signs of past major mergers but somehow retained enough gas to rebuild their disks. Certain ellipticals, known as rejuvenated galaxies, steal gas from neighbors to spark brief rounds of late-life star formation. Even more puzzling are lenticular galaxies, hybrids with a disk-like spirals but no spiral arms, suggesting they're spirals that ran out of fuel or ellipticals that somehow accreted new gas. What's fascinating is that we're watching this divergence happen in real time. The Atacama Large Millimeter Array has spotted dead spirals in the distant universe galaxies that shut down star formation early, possibly on their way to becoming compact ellipticals. Meanwhile, the Hubble Space Telescope has caught young ellipticals still reeling from violent mergers, their shapes not yet fully settled. These observations confirm that a galaxy's fate isn't sealed at birth. It's shaped by a lifetime of cosmic interactions, with every collision, gas theft, and burst of star formation leaving its mark. Ultimately, the difference between spirals and ellipticals isn't just about appearance, it's about how they've lived. Spirals are the marathon runners, pacing themselves with steady gas consumption over eons. Ellipticals are the sprint champions, burning through their fuel in spectacular bursts before fading into a golden retirement. Both are equally majestic, equally vital to the cosmic story, and equally mesmerizing reminders that in the grand galactic tapestry, no two threads follow quite the same path. Spiral galaxies are cosmic masterpieces, their delicate arms unfurling like celestial whirlpools across the darkness. But this exquisite structure demands precise conditions, a rare cosmic recipe where gas, gravity, and time must align perfectly. Unlike their elliptical cousins born from violent mergers, spirals emerge from quieter beginnings, where a rotating disk of gas can persist undisturbed for billions of years. The foundation lies in the gas reservoir. Spiral galaxies are voracious consumers of hydrogen, constantly replenishing their supplies from delicate filaments of intergalactic material. This gas must remain cool enough to avoid boiling away, yet turbulent enough to resist collapsing all at once. Picture a spinning ice skater. The faster they rotate, the more their arms extend outward. Similarly, a protogalaxy's initial rotation flattens its gas into a disk, creating the stage for spiral arms to form. But rotation alone isn't enough. The gas must also avoid catastrophic disruptions, like collisions with other large galaxies that could scramble its orderly motion into chaos. Dark matter plays a silent but crucial role here. A well-ordered halo of dark matter envelops the gas disk, stabilizing it against external disturbances. Computer simulations show that lopsided or turbulent dark matter halos can warp or even shred delicate gas disks, preventing spiral formation. The Milky Way's halo, for instance, is remarkably symmetrical. a cosmic shield that's allowed our galaxy's spiral arms to endure for eons. Star formation within these disks follows an intricate rhythm. Density waves like traffic jams in the flow of orbiting gas create the iconic spiral patterns. As gas piles up in these waves, it triggers bursts of star formation, lighting up the arms in brilliant blue. But there's a delicate balance. Too many massive stars and their supernova could blow away the remaining gas. Too few, and the spiral structure fades. The sweet spot produces just enough stars to maintain the pattern without exhausting the fuel supply. What's fascinating is how resilient yet fragile this equilibrium can be. Some spirals, like grand design galaxies with two sweeping arms, maintain near-perfect symmetry for billions of years. Others, like flocculent spirals, have patchy, fragmented arms suggesting more turbulent pasts. Even subtle differences in a galaxy's merger history leave fingerprints. The Andromeda Galaxy's warped disk hints at a long-ago encounter with a smaller companion, while the Whirlpool Galaxy's flawless arms show an almost untouched existence. But the true test of a spiral's endurance comes when faced with the universe's crowded environments. In dense galaxy clusters, spirals often lose their gas to a process called ram pressure, stripping like leaves torn from trees by a strong wind. This explains why most spirals live in cosmic suburbs, while cluster centers are dominated by gas-poor ellipticals. Our Milky Way resides in the relatively quiet local group, a cosmic backwater where it's avoided catastrophic collisions just long enough to perfect its spiral dance. Yet spirals aren't static. Even now, the Milky Way's arms slowly wind tighter, their patterns evolving as stars migrate over time. Some theorists suggest our galaxy may have looked more like a barred spiral in its youth, with a straight central feature that later smoothed into today's graceful curves. Others speculate that all spirals eventually transform, whether through slow exhaustion of gas or a fateful future merger. For now, though, they remain the universe's most enduring works of art, their spiral arms writing the story of galactic evolution in starlight and hydrogen. The swirling arms of spiral galaxies don't form by accident. Their elegant structure comes from one of the universe's most fundamental forces, angular momentum. Picture a figure skater pulling their arms in to spin faster, or a diver tucking tight to complete rapid rotations. This same principle, applied on a galactic scale, shapes how gas clouds transform into spinning cosmic disks. When a massive gas cloud begins collapsing under its own gravity, any slight initial rotation gets amplified dramatically, like a pebble creating ripples that grow into waves. This isn't just an interesting side effect, it's the physics that makes spiral galaxies possible. Consider the sheer scale of this process. A primordial gas cloud might start with barely any rotation, just a gentle drift compared to its enormous size. But as gravity pulls everything inward, conservation of angular momentum kicks in. Just like that spinning skater, the cloud rotates faster as it shrinks, forcing the material to flatten into a disk perpendicular to the spin axis. Most of the mass collects toward the center, forming the galaxy's bright bulge, while the remaining gas spreads into a vast, thin sheet that becomes the breeding ground for spiral arms. Without this rotational braking system, galaxies would collapse into formless blobs rather than the intricate structures we admire. The numbers behind this transformation are staggering. A typical spiral galaxy like the Milky Way completes one full rotation every 200 million years, yet its stars don't move in perfect circles. The outer regions rotate more slowly than the inner ones, creating a differential rotation that stretches and wins any density variations into spiral patterns. Computer simulations show this beautifully. When researchers model collapsing gas clouds with initial spin, spiral structures emerge naturally within a few rotations, no extra ingredients required. The Great Barred Spiral Galaxy, NGC 1300, demonstrates this perfectly, with arms that appear to unwind from its central bar like streamers caught in a cosmic breeze. But angular momentum does more than shape galaxies, it preserves their structure over billions of years. Stars orbiting too close to the center get drawn into the bulge, while those too far risk being flung outward. The sweet spot lies in the disk itself, where balanced forces allow stars and gas to maintain stable, nearly circular orbits. This stability explains why spiral galaxies can persist for so long, their patterns enduring even as individual stars complete hundreds of laps around the galactic center. Yet mysteries remain. Some galaxies rotate far faster than their visible mass should allow, a discrepancy that first hinted at the existence of dark matter. Others, like the stunning Pinwheel galaxy, show nearly perfect symmetry in their arms, suggesting remarkably undisturbed histories. Even more puzzling are counter-rotating disks, where inner and outer regions spin in opposite directions, likely the result of complex mergers that somehow preserved angular momentum in unexpected ways. Each discovery reminds us that while the basic physics is universal, its application across the cosmos produces endless variations, a testament to both the predictability of physical laws and the creativity of nature. The next time you see an image of a spiral galaxy, remember you're not just looking at a random arrangement of stars, you're witnessing the visible legacy of angular momentum, a force so reliable it can turn chaos into beauty, and so persistent that its influence echoes across billions of light years. From the smallest pirouette to the grandest galactic dance, the universe keeps perfect balance, spinning its wonders into existence one revolution at a time. Those breathtaking spiral arms you see in galaxies aren't fixed structures, they're cosmic illusions, patterns that move through the galactic disk like ripples in a pond. Imagine traffic flowing on a highway where cars slow down as they pass through construction zones, bunching up temporarily before speeding away. That's essentially how density waves work in galaxies. The arms aren't made of the same stars and gas forever. Instead, they're regions where material piles up as it orbits, creating the illusion of permanent structure while individual stars drift in and out like commuters passing through a bottleneck. At the heart of this phenomenon is a delicate interplay between gravity and motion. As stars and gas clouds orbit the galactic center, they encounter regions where the gravitational pull is slightly stronger, often due to asymmetries in the galaxy's central bar or the collective tug of nearby stars. These gravitational hotspots act like invisible speed bumps, slowing down the material that passes through them. The result, a wave of compressed gas that moves through the disk at a different speed than the stars themselves. It's akin to a sound wave traveling through air. The air molecules don't travel with the wave, they just vibrate in place as the wave moves past. This compression has spectacular consequences. When gas clouds enter a spiral arms density wave, they're squeezed tightly enough to collapse under their own gravity, igniting new stars. That's why spiral arms appear so bright. They're lined with young, hot stars that formed in these cosmic pressure cookers. But here's the twist, those stars don't stay in the arms forever. As they're born, they continue orbiting, gradually drifting ahead of the slower moving wave while fresh gas enters behind them. Over millions of years, the stars that made an arm glow will disperse, only for new ones to take their place. The spiral pattern persists, but the players are always changing. The Milky Way offers a perfect case study. Our galaxy's major spiral arms, like the Perseus arm or the Scutum Centaurus arm, aren't solid, unchaining rivers of stars. Radio telescopes mapping hydrogen gas reveal how material flows into these regions, gets compressed, and triggers star formation before moving on. The Orion Spur, where our solar system resides, is a minor offshoot of this process, a testament to how even smaller density fluctuations can shape local star-forming regions. Density waves also explain why some spiral arms appear tighter or looser than others. In galaxies with fast-rotating inner disks, the waves wind up quickly, creating tightly wrapped arms. In others, like the Grand Design Spiral Messier 81, the pattern stays open and smooth, suggesting a more gradual wave speed. Even galactic collisions can alter the rhythm. When the Whirlpool galaxy interacted with its neighbor, the gravitational disturbance sent a density wave rippling through its disk, lighting up its arms in a burst of fresh stellar birth. But the theory isn't without its puzzles. Some flocculent spirals with their patchy, disjointed arms don't fit the classic density wave model neatly. Computer simulations suggest these might emerge from local instabilities rather than galaxy-wide waves, showing how star formation itself can sometimes carve spiral-like patterns without a grand underlying design. And in galaxies with especially active cores, jets from supermassive black holes can plow through gas disks, creating spiral shocks that mimic density waves in surprising ways. What's mesmerizing is how this process connects the largest and smallest scales of star formation. A single spiral arm might stretch tens of thousands of light years, yet its influence boils down to individual gas clouds collapsing under pressure, a chain reaction where galactic mechanics birth stellar nurseries. And because these waves recycle gas over time, they ensure galaxies don't burn through their fuel all at once, extending their star-forming lives across billions of years. The next time you gaze at a spiral galaxy's graceful arms, remember, you're not just seeing a static portrait, you're witnessing a dynamic, ever-shifting performance, one where gravity writes the music and stars dance to its rhythm. Spiral arms serve as the galaxy's most fertile star-forming nurseries, where clouds of gas collide and compress under immense pressure, igniting the brilliant blue-white stars that trace these cosmic swirls. Picture a vast interstellar traffic jam. Particles pile up as they enter the dense spiral wave, squeezed so tightly that gravity finally overcomes their resistance. Hydrogen atoms, once drifting light years apart, are forced into close quarters, their collisions growing more frequent and violent until nuclear fusion sparks to life. This process doesn't just create a few scattered stars, it spawns them by the millions, clustering them along the arms like diamonds strewn across velvet. The physics behind this stellar boom is both elegant and relentless. As gas flows into the spiral arm's density wave, it's funneled into shock fronts, regions where pressure spikes abruptly. These shock zones act like cosmic anvils, hammering loose gas into dense, star-forming clumps known as molecular clouds. The Orion Nebula offers a nearby glimpse of this phenomenon, a stellar nursery where young stars blaze within twisted filaments of gas, their intense radiation sculpting the surrounding material into glowing caverns. But spiral arms amplify this effect across entire galaxies, turning isolated star-forming regions into sprawling production lines. What's remarkable is how efficiently spiral arms recycle their fuel. The same shock fronts that trigger star formation also channel remaining gas back into the interarm regions, where it cools and gathers for another pass through the density wave. This cyclical process ensures galaxies don't exhaust their star-making material too quickly, sustaining spiral patterns for billions of years. The Milky Way's own Carina arm demonstrates this beautifully, with its mix of newborn stars and lingering gas clouds poised to birth the next generation. Massive stars play a paradoxical role in this cycle. Their searing ultraviolet radiation and powerful stellar winds blast away nearby gas, seemingly stifling further star formation. Yet these same forces also compress adjacent clouds, triggering new rounds of collapse. It's a self-regulating system, like a forest where wildfires clear space for new growth. Supernovae add another layer, their shockwaves injecting heavy elements into the interstellar medium while carving bubbles that eventually spawn fresh stellar clusters. The visual signature of this activity is unmistakable. Spiral arms glow brightest in ultraviolet and blue light, the telltale hues of hot, young stars. Infrared observations reveal the darker side of the story, vast dust lanes where gas is still condensing, hidden from optical view but teeming with future potential. Even the subtle color gradients along an arm tell a story, with the youngest stars clustered near the leading edge where compression is strongest, while older, redder stars trail behind like breadcrumbs marking the passage of time. Yet not all spiral arms are equally productive. The Scutum Centaurus arm in our galaxy is a star-forming powerhouse, while the Perseus arm shows more subdued activity. These variations hint at differences in gas density, shear forces, or even past collisions that reshape the local environment. Some galaxies, like the flocculent spiral NGC 2841, form stars in patchy, disjointed clusters instead of organized arms, proving that while density waves are efficient, they're not the universe's only method for stellar birth. What's truly humbling is realizing our own solar system likely formed in a spiral arms compression zone billions of years ago. The same forces that light up galactic arms with young stars may have set the stage for Earth's eventual creation. Every element heavier than hydrogen in our bodies was forged in such stellar factories, making spiral arms not just beautiful features of distant galaxies, but essential chapters in our own cosmic ancestry. Their glow isn't merely a spectacle, it's a testament to the universe's relentless creativity, turning chaos into light, one compressed gas cloud at a time. At the heart of nearly every galaxy lies a gravitational monster, a supermassive black hole millions or even billions of times heavier than our Sun. These cosmic titans aren't just passive anchors around which galaxies spin. They are active participants in the galactic drama, shaping their homes through colossal outbursts of energy that can either ignite or extinguish star formation across vast regions. Their influence is so profound that without these black holes, many galaxies might look completely different, or perhaps not exist at all in their current forms. Take quasars, for instance, the brightest objects in the universe. When a supermassive black hole actively feeds on surrounding gas, the material doesn't just vanish quietly. As it spirals inward at nearly light speed, friction heats it to millions of degrees, creating a swirling disk of plasma that outshines the galaxy itself. The radiation blast from such a disk can travel hundreds of thousands of light years, ionizing gas across the entire galaxy and rendering it too energetic to collapse into new stars. It's like a cosmic blowtorch vaporizing a cloud. The raw material is still there, but now too agitated to form anything. But black holes don't just say no to star formation, they sometimes say not here. Their relativistic jets, narrow beams of particles shot outward at nearly light speed, can plow through galactic gas like a pressure washer, clearing huge cavities. The shock waves from these jets compress the remaining gas at their edges, triggering bursts of star formation in precise rings around the empty zones. The nearby galaxy Messier 87 shows this beautifully, with its famous jet stretching thousands of light years and its surrounding regions peppered with young star clusters where the jet's energy has sculpted the interstellar medium. This feedback mechanism acts like a galactic thermostat. When too much gas flows toward the center, feeding frenzies create quasar activity that shuts down widespread star formation. As the galaxy's gas reservoir depletes, the black hole quiets down, allowing remaining gas to cool and form stars again, until the cycle repeats. Computer simulations now suggest this push and pull is why we don't see many galaxies with the absurdly high star formation rates expected in the early universe. The black holes, in effect, prevent their host galaxies from burning out too quickly. The most extreme examples occur in galaxy clusters, where supermassive black holes pump energy into their surroundings on mind-boggling scales. The Perseus cluster's central black hole has created bubbles in the hot cluster gas so large they could swallow our entire galaxy, each powered by outbursts equivalent to millions of supernovae. Yet even these titanic explosions serve a purpose. Without them, the cluster's gas would have cooled and collapsed long ago, forming far more stars than we observe. It's a delicate balance between chaos and order, destruction and creation, all orchestrated by these gravitational powerhouses. Astoundingly, the black holes themselves seem to grow in lockstep with their galaxies. Observations show that the mass of a central black hole typically correlates with the mass of its host galaxy's bulge, not because the black hole controls the bulge directly, but because both depend on the same gas supply. More gas means more stars in the bulge and more food for the black hole, linking their fates inextricably. This cosmic symbiosis suggests that to understand how galaxies form and evolve, we must first reckon with the monsters lurking in their cores. Yet mysteries persist. Some galaxies with supermassive black holes show little signs of feedback, while others seem dominated by it. The Milky Way's own Sagittarius is currently dormant, its last major outburst occurring perhaps 2 million years ago, a blink in cosmic time. And in the early universe, some black holes grew to billions of solar masses shockingly fast, far outstripping their host galaxy's growth. These outliers challenge our models, reminding us that the dance between galaxies and their central black holes has variations we're only beginning to comprehend. What's clear is that black holes are anything but destructive parasites, their architects, sculpting the galaxies around them through cycles of violence and calm. Their outbursts create the conditions for both star formation and star suppression, ensuring galaxies evolve neither too fast nor too slow. Without these gravitational titans at their hearts, the universe might lack the diversity of galaxies we see today. No majestic spirals, no glowing ellipticals, just an ocean of gas and stars without structure or rhythm. So the next time you gaze at a galaxy's glowing center, remember, there's more than darkness there. There's a conductor silently shaping the symphony of stars around it. Barred spiral galaxies add a fascinating twist to galactic structure, literally. Unlike classic spirals with arms sweeping directly from the core, these galaxies sport a straight, rigid bar of stars cutting through their centers, with spiral arms curling away from the ends like cosmic ribbons. This isn't just an aesthetic quirk. That bar acts as a gravitational funnel, channeling gas inward in one of the universe's most efficient cosmic conveyor belts. The process begins with instability. As stars orbit within a spiral galaxy, their collective gravity can amplify small asymmetries over time, causing orbits to align into an elongated bar shape. Once formed, this structure becomes a self-perpetuating engine, reshaping the galaxy's inner dynamics entirely. Gas caught in the bar's grasp follows a dramatic journey. As clouds drift toward the bar, its rotating gravitational field shepherds them along like a celestial traffic cop, redirecting their paths toward the galactic center. The effect is strikingly visible in infrared observations of barred galaxies like NGC 1097, where dust lanes trace the inward flow like streaks of ink spiraling down a drain. This migration doesn't happen smoothly. Gas piles up at orbital resonances, regions where the bar's rotation synchronizes with the natural frequencies of orbiting material. These bottlenecks create shock fronts that compress the gas, igniting starbursts along the bar's length while reserving the richest fuel deposits for the galaxy's heart. The consequences are transformative. Central regions of barred galaxies often glow with intense star formation, their cores crowded with young stellar clusters thanks to this steady influx of gas. But the bar's influence doesn't stop there. By funneling material toward the supermassive black hole lurking at the center, it can awaken dormant giants. Hubble images of barred galaxies frequently show active nuclei blazing with the telltale radiation of infalling matter, a direct result of the bar's gravitational plumbing. The Milky Way's own modest bar, discovered through painstaking star motion studies, may have played a role in feeding Sagittarius during past epochs of activity. What's remarkable is how bars evolve over time. Computer simulations suggest they're not permanent structures. As a bar drives gas inward, the resulting changes in mass distribution can gradually weaken it, like a paddle losing its shape after stirring thick batter for too long. Some bars eventually dissolve, leaving behind a lens-shaped structure called a pseudobulge, while others may regenerate through new instabilities. This cyclical behavior implies that barred spirals might represent a dynamic phase in galactic middle age, a transitional state between disordered youth and the settled maturity of unbarred spirals or ellipticals. Yet bars aren't one size fits all. Some galaxies, like the spectacular NGC 1300, showcase grand design bars with symmetrical, well-defined arms, while others sport messy, irregular versions. The strength of the bar, how elongated and gravitationally dominant it is, also varies dramatically. Weak bars gently nudge gas along, while strong ones create veritable rivers of inflow capable of draining a galaxy's outer regions over billions of years. These differences likely stem from each galaxy's unique history of mergers, gas accretion, and internal dynamics. The broader implications reshape our understanding of galactic ecosystems. Bars may explain why some galaxies exhaust their star-forming fuel faster than others, their efficient central funneling leaving outer regions gas-poor. They also provide a plausible mechanism for growing supermassive black holes in galaxies without violent mergers quiet, sustained feeding via the bar pipeline rather than dramatic collision-driven feasts. Observations of distant barred galaxies show these structures were already in place when the universe was half its current age, proving their role in shaping cosmic evolution spans eons. For astronomers, barred spirals serve as natural laboratories. Their predictable structure allows precise measurements of galaxy rotation and mass distribution, while their gas flows offer real-time views of processes that might otherwise happen too diffusely to observe. Even our own Milky Way's bar, initially controversial, now provides crucial clues about our galaxy's past and future. The next generation of telescopes promises to reveal bars in even younger galaxies, helping us understand when and how these cosmic regulators first emerged to stir the galactic pot. Their presence reminds us that galaxies aren't static islands, they're dynamic systems where simple gravitational rules can produce breathtaking complexity, one rotating bar at a time. Galaxies aren't gentle neighbors, they're cosmic predators, consuming smaller companions in a slow-motion feast that spans billions of years. The Milky Way is no exception. Right now, it's tearing apart the Sagittarius dwarf galaxy, stretching its stars into a shimmering stream that wraps around our galactic disk like a celestial serpent. This isn't destruction, it's transformation. Every time a large galaxy absorbs a smaller one, it gains not just stars but precious gas, dark matter, and even pre-made star clusters, fueling its continued growth and evolution. The process begins with gravity's relentless pull. When a dwarf galaxy ventures too close to a giant like the Milky Way, tidal forces stretch it like taffy, peeling away stars and gas in long filaments called tidal streams. These cosmic breadcrumbs, visible in sensitive sky surveys, mark the death throes of galaxies too small to survive. The large Magellanic Cloud currently orbiting the Milky Way faces the same fate. Despite containing billions of stars, it's steadily losing material to our galaxy's gravitational pull, its gas forming a shimmering bridge between the two systems. But size isn't the only factor. A galaxy's trajectory determines how it's digested. Head-on collisions trigger dramatic bursts of star formation as gas clouds smash together, while gradual mergers, like the Milky Way's ongoing consumption of the Canis Major dwarf, allow stars to be assimilated more quietly. Some small galaxies pass through larger ones multiple times before fully disintegrating, each orbit stripping away another layer like an apple being peeled in slow motion. The aftermath leaves lasting fingerprints. When astronomers map the Milky Way's outer halo, they find stars moving in odd, clustered orbits, the galactic equivalent of undigested bones. These stellar fossils, like those in the Gaia Enceladus stream, betray past mergers so ancient their original galaxies no longer exist as coherent structures. Chemical analysis reveals even more. Stars born in different galaxies have distinct elemental signatures, allowing astronomers to trace their origins like cosmic genealogists. Elliptical galaxies showcase cannibalism's most spectacular results. Behemoths like Messier 87 grew to their enormous sizes by swallowing dozens of smaller galaxies, their random stellar orbits reflecting this violent history. Some even contain multiple supermassive black holes, legacies of past mergers where the central giants haven't yet fully coalesced. The antennae galaxies offer a snapshot of this process mid-meal. Their two cores still separate but already entwined in luminous tendrils of newborn stars. Yet mergers aren't just about growth, they're also catalysts for change. When a gas-rich dwarf plunges into a spiral galaxy, it can disrupt the delicate disk, triggering waves of star formation or even igniting the central black hole. Other times, mergers inject fresh gas into aging ellipticals, briefly resurrecting their ability to form stars. The universe constantly reinvents itself through these interactions, turning destruction into creation on the grandest scales. Our own galaxy's future is written in these dynamics. In about 4 billion years, the Milky Way will collide with Andromeda, merging into a single elliptical galaxy astronomers have nicknamed Milkdromeda. Simulations show the two spiral structures tangling and dissolving, their stars flung into new orbits while their central black holes circle each other in a gravitational dance. Yet even this cataclysm won't be the end. Galactic cannibalism ensures the universe's largest structures keep growing, feasting, and evolving until the last stars fade from the sky. The Milky Way story begins not with a grand entrance but with a whisper, a faint gathering of hydrogen and helium in the darkness of the early universe. Over 13 billion years ago, long before Earth or even the Sun existed, our galaxy was nothing more than a hazy patch of gas, barely denser than its surroundings. Yet within that subtle imbalance lay the seeds of everything to come. Gravity, patient and relentless, began pulling these sparse atoms together, drawing them into clumps that would one day become the Milky Way's first building blocks. These primordial fragments weren't the majestic spiral we know today. They were messy, irregular clouds of gas and dark matter, chaotically colliding and merging. Among them was Gaia Enceladus, a dwarf galaxy whose name now graces one of the Milky Way's most famous stellar streams. When it smashed into our infant galaxy nearly 10 billion years ago, the collision sent stars scattering like billiard balls, their orbits forever altered. Today, we can still trace these ancient rebel stars moving backward or at odd angles through the galactic halo, their chemical fingerprints betraying their violent origins. As mergers continued, something remarkable happened. Rotation emerged. Like water circling a drain, the Milky Way's gas began spiraling inward, flattening into a disk under the influence of angular momentum. This was the birth of our galaxy's iconic structure, but it wasn't yet the graceful spiral we see now. Early models suggest the Milky Way may have started as a clumpy, irregular disk, its stars and gas unevenly distributed like lumps in a bowl of batter. Only over billions of years did these irregularities smooth out, sculpted by the same gravitational forces that had created them. Star formation played a crucial role in this transformation. The first generations of stars, forged from pristine hydrogen and helium, lived fast and died violently. Their supernova enriched the surrounding gas with heavier elements, oxygen, carbon, iron, seeding future stellar generations with the ingredients for planets and eventually life. Astronomers have found relics of these early stars in the Milky Way's halo, ancient suns so metal-poor, they're little more than hydrogen and helium with a sprinkle of heavier elements. They're living fossils offering clues about our galaxy's chemical infancy. The spiral arms came later. As the disk stabilized, density waves began moving through it like ripples in a pond, compressing gas and triggering bursts of star formation. These patterns didn't stay static, they evolved, with some arms tightening while others unwound. The Milky Way's current structure, with its 4 major arms and several minor spurs, reflects this dynamic history. Our solar system resides in the Orion Spur, a relatively quiet branch between the Perseus and Sagittarius arms, its position perhaps influenced by long-ago interactions with passing dwarf galaxies. Central to this evolution was the Milky Way's supermassive black hole, Sagittarius A. Though quiet now, evidence suggests it was once an active quasar. Its intense radiation-shaping gas flows across the galaxy. Its gravity also plays a stabilizing role, anchoring the surrounding stars in predictable orbits that maintain the galactic bulge's distinctive peanut shape. But the Milky Way's story isn't finished. Even now, it continues to consume smaller galaxies, with the Magellanic Clouds and the Sagittarius Dwarf steadily contributing stars and gas. In the distant future, its collision with Andromeda will rewrite its structure entirely. Yet for all these grand transformations, what's most astonishing is how stable our galactic home has remained over billions of years, a testament to the delicate balance between chaos and order that governs the universe. Every star we see at night, every spiral arm traced in telescope images, carries echoes of this epic history, reminding us that galaxies aren't just places in space. They're living records, their light telling stories of birth, destruction, and rebirth on scales almost too vast to comprehend. The Milky Way doesn't travel through space alone. It's surrounded by an entourage of smaller satellite galaxies, each playing a subtle but vital role in shaping our cosmic home's evolution. The most famous of these companions, the large and small Magellanic Clouds, are more than just picturesque smudges in the southern sky. They're active participants in a gravitational dance that's altering the Milky Way's structure in real time. These dwarf galaxies orbit our own like moths circling a flame, their paths weaving through the dark matter halo that envelops our galaxy, leaving trails of stars and gas in their wake. Right now, the large Magellanic Cloud is yanking on the Milky Way's dark matter halo with enough force to warp our entire galactic disk. Astronomers first noticed this distortion in the 1950s when mapping hydrogen gas, discovering that the Milky Way's disk isn't perfectly flat. It's twisted like a vinyl record left too long in the sun. Recent studies using the Gaia Space Telescope reveal this warp isn't static. It precesses around the galactic center, oscillating as the Magellanic Cloud's gravity tugs at different angles over time. The effect is like spinning a dinner plate while balancing it on a stick. Subtle nudges create ripples that travel outward in slow motion. But the Magellanic Clouds aren't just passive disruptors, they're also victims of the Milky Way's relentless pull. A vast river of hydrogen gas, known as the Magellanic Stream, stretches across a quarter of the night sky, trailing behind the 2 dwarf galaxies like a cosmic wake. This gas didn't leak out gradually, it was torn away by our galaxy's tidal forces over billions of years, leaving a filament of material so extensive it takes light nearly 200 million years to travel from one end to the other. The Milky Way is steadily siphoning this gas, funneling it toward the galactic disk where it will eventually fuel new generations of stars. The small Magellanic Cloud shows particularly dramatic scars from this interaction. Its shape is wildly distorted, resembling a taffy pull stretched between 2 competing forces, the Milky Way's gravity versus its own momentum. Infrared observations reveal a turbulent interior where gas clouds collide violently, triggering bursts of star formation in unpredictable patterns. Unlike the orderly spiral arms of our galaxy, the small Magellanic Cloud star-forming regions look like scattered embers, their chaos a direct consequence of the relentless tidal forces acting upon them. These interactions aren't just temporary disturbances, they're shaping the Milky Way's future. Computer simulations predict the Magellanic Clouds will eventually merge with our galaxy, their stars becoming part of the Milky Way's halo while their gas replenishes the disk's star-forming reserves. Some models even suggest the large Magellanic Cloud's current orbit might send it crashing through the Milky Way's disk in about 2 billion years, an event that would ignite fireworks of star formation visible across intergalactic space. Beyond the Magellanic Clouds, dozens of fainter satellite galaxies orbit the Milky Way, each leaving its own subtle imprint. The Sagittarius dwarf spheroidal, discovered in the 1990s, is currently being torn apart, its stars strewn across the sky in vast, looping streams. The ultra-faint dwarfs like Segway 1, barely brighter than a globular cluster, might be primordial relics, galactic building blocks that never fully merged, preserving clues about the universe's first structures. What's fascinating is how these satellites influence the Milky Way's chemistry. Stars born in dwarf galaxies have distinct elemental signatures lower in heavy elements like iron, but sometimes richer in rare isotopes like europium. When these stars join the Milky Way through mergers, they create chemical flavors that astronomers can trace like galactic archaeologists. The Gaia satellite has already identified hundreds of stars in our halo with orbits and compositions matching ancient accretion events, proving the Milky Way grew not just by gathering gas, but by consuming entire galaxies. Yet the story isn't one-sided. Just as the Milky Way shapes its satellites, they too leave their mark. The Magellanic Clouds passage has likely stirred up our galaxy's outer gas reservoirs, preventing it from becoming too settled. Some theories suggest their gravity might even trigger density waves that reinforce spiral arm patterns, making them not just disruptors but collaborators in the Milky Way's grand design. As we peer deeper into the cosmos, we're finding similar satellite systems around other galaxies. Andromeda has at least 30 known dwarfs, some arranged in a vast rotating disk. This suggests the Milky Way's relationship with its satellites isn't unique, but part of a universal pattern where large galaxies grow by orchestrating the slow, inevitable dance of their smaller companions. Every time we study these cosmic minnows, we're glimpsing the incremental processes that built the universe's grandeur, one delicate gravitational interaction at a time. Beyond the glowing spiral arms and bustling star-forming regions lies the Milky Way's ghostly halo, a vast spherical cloud of ancient stars, mysterious globular clusters, and invisible dark matter stretching hundreds of thousands of light-years into the void. This ethereal structure contains some of our galaxy's oldest inhabitants, stellar fossils preserving clues about the Milky Way's violent infancy. Unlike the orderly disk where stars orbit in a flat plane, halo stars move like swarming bees in all directions, their chaotic paths tracing the aftermath of primordial collisions that built our galactic home. The halo's most striking features are its globular clusters, dense balls of up to 1 million stars each, orbiting far beyond the galaxy's bright disk. These celestial relics formed when the universe was less than 1 billion years old, their stars so ancient they contain barely any heavy elements. Omega Centauri, the Milky Way's largest globular cluster, shines like a beacon in the southern sky, its core so packed with stars that a hypothetical planet there would have a night sky dazzling with thousands of suns. These clusters didn't originate in the halo. They were likely stripped from dwarf galaxies consumed by the Milky Way during its growth spurt billions of years ago, becoming permanent celestial souvenirs of galactic cannibalism. Far more mysterious is the halo's dark matter component, outweighing all visible stars and gas by a factor of 10. This invisible cocoon explains why the Milky Way's outer stars orbit faster than Newtonian physics, predicts their motion betraying the gravitational grip of unseen mass. Simulations suggest dark matter halos formed first in the early universe, their gravitational wells directing where gas collected and galaxies sprouted. Without this hidden scaffolding, galaxies like ours would never have achieved their majestic sizes, their stars drifting apart like smoke in the wind. The halo also serves as a cosmic dumping ground for stellar outcast stars flung from the galactic disk by violent encounters. Hypervelocity stars race through the halo at speeds exceeding 1 million miles per hour, ejected when binary star systems wandered too close to the supermassive black hole at the Milky Way's heart. Even our Sun carries a halo connection. Its orbit periodically takes it above and below the galactic plane, surfing through this sparse stellar population that contains many stars moving in the opposite direction to the Milky Way's rotation. What makes the halo truly indispensable to astronomers is its role as a time capsule. While the galactic disk continuously recycles its gas and forms new stars, the halo remains largely unchanged, preserving chemical signatures from the universe's first stellar generations. Stars like He 1523-0901, found in the halo with iron abundances 200,000 times lower than our Sun, offer direct windows into the chemical conditions before planets or life could exist. Their pristine compositions match theoretical predictions of the very first stars that flickered to life after the cosmic dark ages. Modern surveys like the Gaia spacecraft are revealing the halo's dynamic nature in unprecedented detail. Instead of a smooth, uniform sphere, we're discovering intricate substructures, streams, shells, and clumps that betray past accretion events. The Sagittarius Stream, a river of stars torn from a devoured dwarf galaxy, wraps around the Milky Way like a celestial serpent, its very existence proving our galaxy grows by consuming smaller neighbors. Another structure, dubbed the Gaia Sausage, consists of stars moving on highly radial orbits, the debris from a head-on collision with a massive dwarf galaxy 8 to 10 billion years ago that may have triggered the Milky Way's disk formation. These remnants tell a story of hierarchical growth, the idea that galaxies build up through countless mergers over cosmic time. The halo isn't just a static relic, it's an active archaeological site where each stellar population marks a different chapter in our galaxy's biography. Current estimates suggest the Milky Way's halo contains the shredded remains of at least 6 substantial dwarf galaxies and dozens of smaller ones, their stars now indistinguishable from native halo stars except through meticulous chemical tagging. Yet the halo may hold even greater surprises. Some theorists propose it could harbor rogue planets ejected from the galactic disk, or even primordial black holes formed in the Big Bang's aftermath. Others speculate that certain dark matter interactions might produce faint gamma-ray glows detectable at the halo's outer edges. As next-generation telescopes like the Vera Rubin Observatory begin surveying the halo in greater depth, we may uncover phenomena that force us to rethink galactic evolution entirely. The Milky Way's halo reminds us that a galaxy is more than its bright disk. It's an ecosystem spanning vast scales, where the visible and invisible intertwine to shape cosmic history. Every time astronomers study these lonely outlying stars, they're not just mapping space, they're excavating time, peeling back layer after layer of galactic ancestry written in starlight and shadow. Galaxies might seem like isolated islands in the vast cosmic ocean, but they're actually voracious consumers, perpetually feeding on fresh gas from the space between them. This invisible rain of intergalactic hydrogen is the lifeblood of star formation, a slow but steady trickle that replenishes what galaxies lose to supernova or lock away in aging stars. Imagine a towering tree in a rainforest. The visible trunk and branches represent the galaxy's stars and dust, while the roots spread unseen, constantly drawing nourishment from the soil. For galaxies, those roots extend into the cosmic web, a network of gas filaments stretching across the universe like an intricate vascular system. The process begins with the faintest wisps of hydrogen left over from the Big Bang drifting through the voids between galaxies. These atoms don't fall in randomly, they follow the dark matter scaffolding that's been in place since the universe's infancy. As gas approaches a galaxy's halo, it cools and condenses, forming streams so tenuous they'd make Earth's best vacuum chambers look crowded. The Hubble Space Telescope has spotted these cosmic tributaries in action around distant galaxies, their presence revealed by the way they absorb light from background quasars, like shadows cast on a celestial lantern. Some galaxies drink this intergalactic rain in delicate sips. Spiral galaxies like the Milky Way often accrete gas gradually, with the material settling into their disks and fueling steady star formation over billions of years. Others gulp it down in violent feasts, especially in the early universe, where massive filaments of gas plunged directly into galactic cores, triggering frenzied starbursts visible across billions of light years. The Spiderweb Galaxy, observed as it appeared when the universe was just 3 billion years old, shows this process in extreme form, with dozens of smaller galaxies embedded in a glowing net of freshly accreted gas. But there's a twist. Not all gas makes it safely to the galactic dinner table. As incoming hydrogen falls toward a galaxy, it can heat up dramatically, especially in massive systems with powerful gravity. The resulting hot gas halos, detected by X-ray telescopes around galaxies like Andromeda, act like cosmic radiators, sometimes preventing cool gas from reaching the star-forming regions below. This creates a balancing act: too much cooling, and the galaxy burns through its fuel too quickly; too little, and star formation stalls entirely. The most dramatic feeding events leave unmistakable scars. When galaxies collide, their gravitational interactions can funnel gas toward their centers in spectacular bursts, simultaneously igniting star formation and feeding supermassive black holes. The nearby Centaurus A galaxy showcases this duality, with vast dust lanes marking recent gas accretion and jets of material shooting from its active nucleus, a testament to the complex relationship between galactic meals and black hole snacks. Interestingly, our own Milky Way is currently dining on two distinct gas sources. High-velocity clouds, first discovered in the 1960s, rain down from the galactic halo at speeds up to 300 kilometers per second, while more tranquil flows seep in from the Magellanic Stream. Atomic hydrogen mapping reveals these clouds are enormous, some containing enough material to form millions of suns, yet so diffuse they'd barely register if we flew through them. This constant replenishment solves one of astronomy's long-standing puzzles: how galaxies avoid running out of star fuel. Without fresh gas, even a giant spiral would exhaust its hydrogen reserves in just a few billion years. Instead, the cosmic web provides an almost endless buffet, ensuring galaxies can keep forming stars, albeit at dwindling rates, for nearly the universe's entire lifespan. The implications stretch far beyond single galaxies. Computer simulations now suggest that gas accretion patterns may determine why some galaxies become spirals while others grow into ellipticals. Systems that maintain orderly, cold gas streams tend to preserve their disks, while those that experience chaotic, shock-heated accretion often transform into unstructured ellipticals. Even dark matter plays a role. Its halos govern how and where gas enters, making invisible matter the ultimate galactic gatekeeper. Modern telescopes are revolutionizing our view of this process. The Atacama Large Millimeter Array has spotted gas filaments feeding distant galaxies in the early universe, while the upcoming James Webb Space Telescope will probe the chemical composition of these flows, revealing how pristine intergalactic gas gets enriched with heavier elements over cosmic time. Each observation adds another piece to the puzzle, showing us how galaxies stay alive by reaching beyond their visible borders, drawing sustenance from the universe itself. What's most astonishing isn't just the mechanics of gas accretion, it's the continuity it represents. The hydrogen atoms now drifting toward the Milky Way may have traveled for billions of years, passing through cosmic voids and dark matter cauldrons before finally becoming part of new stars, planets, or perhaps even life. In this way, galaxies aren't just collections of stars, they're dynamic ecosystems, forever cycling material between their shining cores and the vast, invisible networks that sustain them. Quenching the cosmic shutdown of star formation transforms vibrant galaxies into celestial graveyards where new stars no longer rise. While galaxies often begin as bustling stellar factories, various brutal mechanisms can starve them of gas, leaving behind glittering relics where only old red stars remain. One of the most dramatic executioners is AGN feedback, the fury unleashed by a supermassive black hole's feeding frenzy. When too much gas funnels toward a galaxy's core, the central black hole doesn't just quietly consume it, it erupts. The infalling material forms a searing accretion disk, spewing radiation so intense it ionizes surrounding gas, heating it to millions of degrees until it's too energetic to collapse into new stars. The resulting winds blast outward at thousands of kilometers per second, sweeping galactic gas clean like a hurricane scouring a forest. Observations of galaxies like Messier 77 showcase this in action, with X-ray telescopes revealing vast bubbles in the interstellar medium, ghostly cavities carved by black hole outbursts. But black holes aren't the only culprits. In dense galaxy clusters, a process called ram pressure stripping wrenches gas away with staggering force. Picture a galaxy hurtling through the superheated plasma that permeates clusters. The intergalactic medium acts like a torrential headwind, tearing gas from the galaxy's grasp like leaves ripped from a speeding car. The iconic spiral galaxy NGC 4522, known as the Lost Galaxy, displays this trauma vividly. Its once rich spiral arms now appear frayed and gas-deprived, its star formation snuffed out after plunging too close to the Virgo cluster's core. Even more insidious is strangulation, a slower death where a galaxy's gas supply is severed without violent removal. Deprived of fresh hydrogen, the galaxy exhausts its remaining fuel, fading gradually as its youngest stars burn out and only aging red giants persist. Environment plays a decisive role. Galaxies in crowded clusters face higher odds of quenching due to frequent gravitational harassment, close encounters with neighbors that disrupt gas reservoirs or fling it into intergalactic space. The Coma Cluster, a swarm of thousands of galaxies, is littered with quenched ellipticals, their star formation stamped out by relentless interactions. Yet isolated galaxies aren't immune. Some quench from within, their gas depleted by overly efficient star formation or blown away by successive supernova explosions. The ultra-diffuse galaxy Dragonfly 44 tells this story. Despite its size, it forms almost no new stars, its sparse gas reservoir long since evaporated into the void. The aftermath of quenching isn't always final. Rare, rejuvenated galaxies like NGC 4150 defy expectations by reigniting star formation after capturing fresh gas from cosmic filaments or cannibalizing smaller companions. These cosmic phoenixes prove that while quenching may press pause, it doesn't always mean the end. Yet for most galaxies, once the gas is gone, it's gone forever, leaving behind eerie, red-hued islands where starlight no longer flickers to life. This grand cosmic senescence reminds us that galaxies, like stars, have life cycles not infinite, not immutable, but shaped by forces as violent as they are awe-inspiring. A galaxy's destiny isn't written in the stars alone, it's shaped by the neighborhood it calls home. Picture two galaxies born with identical gas reserves and dark matter halos. Place one in a bustling cluster surrounded by hundreds of neighbors and leave the other drifting in an isolated cosmic void. Billions of years later, they'll look nothing alike. The cluster galaxy may have been stripped of its gas, transformed into a red and dead elliptical, while the isolated one thrives as a gas-rich spiral, its star-forming engines still humming. This dramatic divergence stems from environment, the invisible hand guiding galactic evolution through forces as subtle as tidal nudges and as violent as collisions. Dense galaxy clusters act like cosmic pressure cookers where galaxies face relentless challenges. The space between them isn't empty, it's filled with superheated plasma called the intracluster medium, a gas so scorching it emits X-rays. As galaxies orbit the cluster center, this plasma rams into their gas reservoirs at millions of miles per hour, a process known as ram pressure stripping. The result, spiral arms that once brimmed with star-forming fuel get swept clean, leaving behind ghostly trails of orphan gas. The Sombrero Galaxy, perched on the edge of the Virgo cluster, shows this transition in progress, its once lush disk now frayed at the edges, its star formation quenched by the cluster's unforgiving environment. But clusters don't just strip galaxies, they warp them. Proximity to massive neighbors induces tidal forces that stretch and distort galactic shapes. Some galaxies become orphans, ejected from clusters entirely by gravitational slingshots, left to wander intergalactic space like celestial nomads. Others, like the famed jellyfish galaxy JO206, sprout tendrils of gas torn away by these interactions, their star-forming material trailing behind them like cosmic comet tails. Hubble's images reveal blue knots of newborn stars forming within these stripped gas streams, a last burst of creativity before the galaxy's fuel runs dry. Meanwhile, in cosmic voids, the universe's empty backwaters, galaxies lead sheltered lives. Freed from the crowding and violence of clusters, they evolve at their own pace, hoarding gas and forming stars slowly over eons. These void galaxies often appear smaller and bluer than their cluster counterparts, with irregular shapes betraying their lack of gravitational harassment. The galaxy MCG plus 01-0202, one of the most isolated known, floats in a void 300 million light-years wide, its undisturbed disk a time capsule of quieter evolution. Yet isolation isn't always paradise without periodic mergers to stir the pot. Some void galaxies exhaust their gas reserves inefficiently, their star formation sputtering out prematurely. The most extreme environmental influence comes from galaxy groups, small collections where a single dominant galaxy, often a giant elliptical, exerts outsized control. Through a process called galactic cannibalism, these giants consume smaller neighbors, growing while their victims fade. The Milky Way itself is a modest cannibal, currently digesting the Sagittarius dwarf spheroidal galaxy. In groups like Stefan's quintet, we witness this hierarchy in action. Galaxies tangle gravitationally, their gas compressed into brilliant starbursts before the largest member absorbs the rest. Yet environment isn't just about location, it's about timing. Early in the universe, even dense regions were gas-rich, allowing galaxies to form stars rapidly despite crowding. Today, many clusters are red and dead, their gas reservoirs depleted over billions of years of interactions. The Spiderweb galaxy, observed as it appeared 11 billion years ago, reveals an epoch when clusters were still forming, its central galaxy gorging on gas while dozens of smaller galaxies swarm around it, destined to merge into a single behemoth. What's fascinating is how galaxies resist or adapt to their environments. Some cluster galaxies develop thick gas shields or magnetic fields to protect their star-forming regions. Others, like the Phoenix galaxy at a cluster's core, defy expectations by reigniting star formation, possibly by drawing gas from intergalactic filaments that survive the cluster's heat. These outliers prove that while environment sets the rules, galaxies occasionally rewrite them. From the furnace-like centers of clusters to the tranquil expanses of voids, each galactic neighborhood tells a different story. Their varied fates remind us that galaxies aren't just products of their internal physics, they're actors in a grand cosmic play, their evolution scripted by the celestial communities they inhabit. So the next time you gaze at a galaxy's shape or color, remember, you're not just seeing a single object, you're witnessing the imprint of an entire ecosystem, a lifetime of gravitational handshakes and near misses that made it what it is today. Galaxy clusters are the metropolises of the cosmos, vast gravitational hubs where hundreds or even thousands of galaxies congregate, bound together in a shimmering web of dark matter and hot gas. Unlike the solitude of void galaxies, cluster environments are dynamic battlegrounds where galaxies jostle for space, resources, and survival. Here, the rules of evolution change drastically, shaped by forces unseen in quieter cosmic neighborhoods. The most dramatic transformation occurs through RAM pressure stripping, a process as violent as it sounds. Picture a spiral galaxy sailing through the cluster's superheated intracluster medium, a plasma so scorching it glows in X-rays. As the galaxy moves, this intergalactic wind slams into its gas disk like a hurricane against a sail, ripping away the raw material for star formation. The iconic spiral NGC 4522, drifting through the Virgo cluster, bears these scars vividly, its once lush arms now tattered and gas-depleted, its star-forming potential snuffed out by the relentless onslaught. Yet stripping isn't the only hazard. Tidal forces in clusters warp galaxies in ways that defy their original forms. Close encounters with massive neighbors stretch galaxies into grotesque shapes, leaving behind tidal tails, long streams of stars and gas flung into intergalactic space. The Tadpole Galaxy showcases this beautifully, its tail stretching over 200,000 light-years, a cosmic brushstroke painted by gravitational disruption. Even more striking are jellyfish galaxies like J0206, whose star-forming gas is torn into glowing tendrils that trail behind them like ethereal tentacles. Hubble's keen eye has caught these galaxies mid-transformation, their stripped gas igniting pockets of newborn stars even as the galaxy itself bleeds out. The chaos doesn't end there. Galaxy harassment, a term as ominous as the process it describes, sees smaller galaxies repeatedly jolted by gravitational nudges from larger neighbors. Over time, these interactions heat up the stars in a galaxy's disk, causing them to oscillate wildly and puff the galaxy into a featureless blob. This explains why cluster cores teem with elliptical galaxies, their once orderly spirals scrambled beyond recognition by countless gravitational run-ins. The Coma Cluster, a dense swarm of galaxies, serves as a galactic graveyard where few spirals remain, their structures erased by eons of relentless harassment. But clusters don't just destroy, they also create. The same violent interactions that strip gas can compress what remains, triggering starbursts of unimaginable intensity. When galaxies collide within clusters, their gas clouds smash together, igniting fireworks of star formation that outshine entire galaxies. The antennae galaxies, though not in a cluster, illustrate this principle. Their merging cores ablaze with newborn stars, a preview of the creative destruction that unfolds in denser environments. In clusters, these bursts are often short-lived, as the galaxy's remaining gas is quickly exhausted or blown away by supernova winds, leaving behind a glittering but sterile elliptical. Interestingly, not all galaxies succumb equally. Those arriving late to the cluster, called infalling galaxies, often retain their gas longer, their star formation flickering out gradually as they plunge deeper into the cluster's grip. Observations of the Perseus cluster reveal this stratification clearly. Spirals dominate the outskirts, while the core bristles with red, dead ellipticals, a timeline of cosmic assimilation written in starlight. Some galaxies even resist annihilation by hiding their gas in dense molecular clouds, shielding it from the cluster's fury like a desert plant conserving water. The cluster environment also shapes galaxies in subtler ways. The immense gravity of the cluster's dark matter halo can lens background galaxies, twisting their light into arcs and rings, a phenomenon known as strong gravitational lensing. These cosmic mirages aren't just curiosities, they reveal the cluster's mass distribution, helping astronomers map the invisible scaffolding that dictates how galaxies move and evolve within the cluster. The galaxy cluster MAX J0717, with its sweeping arcs of lensed galaxies, demonstrates this interplay between gravity and light, yet clusters aren't static. Over billions of years, they grow by accreting galaxies and even smaller groups, a hierarchical process that mirrors how galaxies themselves form. The Virgo cluster, our local supercluster's heart, is still digesting smaller groups today, its gravitational pull inexorably drawing in neighbors like the Milky Way's own local group. Future observations with next-generation telescopes promise to reveal even more about these cosmic cities, how their environments alter galaxy chemistry, how their central black holes influence evolution, and perhaps even how some galaxies manage to cheat death by stealing gas back from the cluster itself. In the grand narrative of galactic evolution, clusters are the ultimate proving grounds, places where galaxies are forged, transformed, or extinguished by forces far beyond their control. To study them is to witness the universe's relentless creativity, where destruction and rebirth intertwine on scales so vast they humble even the most familiar celestial wonders. Every galaxy in a cluster carries these stories in its stars, its shape, its very survival, a testament to the fierce beauty of cosmic community. The cosmos is far from finished sculpting its galactic masterpieces. The universe's grand story of galaxy evolution still has chapters yet to be written. If we could fast forward billions of years, we'd witness transformations even more dramatic than those that shape today's spirals and ellipticals. At the heart of this future lies an inevitable cosmic dance. The Milky Way and Andromeda, currently separated by 2.5 million light-years, are hurtling toward each other at over 100 kilometers per second. In about 4 billion years, their mutual gravity will overcome this momentum, pulling them into a collision that will rewrite both galaxies forever. This merger won't be the chaotic smash-up it might seem. Galaxies are mostly empty space, their stars so widely scattered that direct stellar collisions will be vanishingly rare. Instead, the encounter will unfold like a slow-motion ballet, with gravity warping both galaxies' shapes over hundreds of millions of years. Computer simulations reveal the stunning details. Andromeda's approach will first stretch the Milky Way's disk, distorting its spiral arms into elongated tidal tails. As the galaxies swing past each other, these tails will splinter off, scattering stars into a luminous halo. Then, like pendulum weights, they'll fall back together, merging their cores in a final embrace. The result, a colossal elliptical galaxy astronomers have nicknamed Milkdromeda, a golden-hued giant where the Milky Way's orderly spiral and Andromeda's majestic arms will exist only as memories. But the merger's true spectacle lies in its star-forming fireworks. When the galaxy's gas clouds collide, they'll compress violently, igniting starbursts so intense they'll outshine both original galaxies combined. For a brief cosmic moment, a few 100 million years, Milkdromeda's core will blaze with newborn stars, their blue-white light overpowering the older stellar population. Yet this frenzy carries a cost. The same collisions that trigger star formation will also funnel vast amounts of gas toward the supermassive black holes at both galaxies' centers. As these black holes feast, they'll unleash quasar-like outbursts, their radiation heating remaining gas to temperatures too high for further star formation. The result is a cosmic paradox. The merger's most fertile period will also plant the seeds of its eventual sterility. Beyond our local group, galaxy evolution will take even stranger turns. Isolated spirals in cosmic voids may continue forming stars at a leisurely pace for hundreds of billions of years, their gas reserves dwindling but never fully exhausted. In dense clusters, galaxies will keep merging until only a few supergiant ellipticals remain, their dark matter halos having absorbed countless smaller neighbors. The universe's accelerating expansion, driven by dark energy, will eventually pull most galaxies beyond the observable horizon, leaving future civilizations, if any exist, with a far emptier sky. Yet the most profound changes may occur within galaxies themselves. Over trillions of years, even the longest-lived stars will exhaust their fuel, leaving behind cooling white dwarfs, neutron stars, and black holes. Galactic disks, no longer replenished by fresh gas, will gradually fade as stellar collisions and gravitational interactions eject remaining stars into the halo. The once vibrant spirals and ellipticals will become dark relics, their light dimmed to near invisibility, their structures dissolved into amorphous clouds of degenerate matter. This grand narrative isn't just speculation. We're already seeing snapshots of these futures across the cosmos. The elliptical galaxy Messier 87, with its 12,000 globular clusters, shows what Milky Way and Andromeda might become, a smooth, featureless giant where no gas remains to birth new stars. The ultra-diffuse galaxies in the Coma cluster hint at how galactic structures unravel over time. Even the Milky Way's current consumption of the Sagittarius dwarf is a microcosm of the processes that will eventually reshape all galaxies. What's humbling is realizing we're witnessing just a single frame in this cosmic movie. The universe has spent 13 billion years building galaxies, and it will spend trillions more dissolving them. Yet in this grand timeline, even Milkdromeda's era will be fleeting, a bright but brief chapter before the slow fade begins. For now, though, the night sky remains a gallery of galactic diversity, a testament to the dynamic processes that have shaped and will continue to shape the universe's most majestic structures. Peering into the depths of cosmic time requires more than just powerful lenses. It demands an arsenal of specialized tools, each designed to capture different whispers from the universe's grand story. The Hubble Space Telescope revolutionized our view by observing galaxies in visible and ultraviolet light, its crisp images revealing intricate structures in nearby galaxies while spotting faint, redshifted smudges that represented infant galaxies billions of light-years away. But Hubble had limitations. It couldn't see through the dense dust clouds veiling stellar nurseries, nor peer deeply enough into the infrared to witness the universe's first galaxies. That's where the James Webb Space Telescope enters the stage. With its gold-plated beryllium mirrors and suite of infrared instruments, JWST acts as a cosmic time machine, detecting heat signatures from galaxies so ancient their light has been stretched into infrared wavelengths by the universe's expansion. Its early observations already shattered expectations, uncovering galaxies too massive and mature to exist in the universe's infancy, hinting that our models of galactic evolution might need rewiring. Yet optical and infrared telescopes only tell part of the tale. To map the invisible hydrogen fueling galaxy growth, astronomers turn to radio telescopes like ALMA, the Atacama Large Millimeter Array. Nestled high in the Chilean desert, ALMA's 66 dish antennas work in concert to detect millimeter wave radiation emitted by cold gas clouds. These observations reveal the hidden skeletons of galaxies, filaments of gas streaming along cosmic webs, protogalactic disks rotating long before stars ignite, and even the turbulent storms within quasars where black holes feast. Meanwhile, facilities like the Very Large Array track magnetic fields threading through galactic arms, showing how these invisible forces sculpt star-forming regions. Spectroscopy transforms these observations from pretty pictures into data-rich treasure troves. By splitting starlight into rainbows of wavelengths, instruments like the Keck Observatory's Deimos spectrograph measure galaxy compositions, motions, and distances with precision. Doppler shifts in spectral lines betray galactic rotation speeds, betraying the grip of dark matter, while emission lines from elements like oxygen and nitrogen chronicle past stellar explosions. Integral field spectrographs, such as those on the Very Large Telescope, go further, capturing thousands of spectra across a single galaxy to create 3D maps of its gas flows and star-forming zones. The newest frontier lies in multi-messenger astronomy, combining these tools with gravitational wave detectors and neutrino observatories. When LIGO detects ripples from colliding black holes, telescopes scramble to pinpoint the event's galactic context, revealing how such mergers influence their surroundings. Upcoming projects like the Rubin Observatory's Legacy Survey of Space and Time will automate this synergy, scanning the entire southern sky every few nights to catch galaxies in the act of transforming, supernova flaring, quasars awakening, or tidal tails stretching during collisions. Human ingenuity doesn't stop at hardware. Supercomputers like NASA's Pleiades run cosmological simulations that recreate galaxy formation from first principles, virtual universes where dark matter halos coalesce and gas follows the laws of hydrodynamics. By comparing these digital galaxies to real observations, scientists stress test theories, uncovering gaps in our understanding, like why simulated galaxies often grow disks too small or stars too quickly. Machine learning now accelerates this process, sifting through petabytes of telescope data to identify rare objects or subtle patterns invisible to human eyes. What's astounding is how these tools reveal galaxies not as static snapshots, but as dynamic systems evolving across cosmic time. Hubble catches mature spirals in their prime, JWST spies their embryonic forms, and radio arrays monitor the lifeblood of gas flowing between them. Together, they weave a narrative far richer than any single instrument could tell, a testament to humanity's relentless curiosity and our growing mastery of the cosmic dance. To understand galaxies, we don't just peer through telescopes, we build entire universes inside supercomputers. These cosmic simulations are laboratories where physicists recreate billions of years of galactic evolution in weeks, testing theories about how dark matter sculpts halos, how gas cools into disks, and how mergers reshape spiral arms into elliptical blobs. The most sophisticated models, like the Illustris TNG project, track trillions of particles representing stars, gas, and invisible dark matter. Their interactions governed by equations encoding everything from nuclear fusion in stars to the explosive feedback of supermassive black holes. What emerges isn't just pretty animation, it's a virtual cosmos so accurate it produces familiar galaxies without cheating, their spiral arms, bulges, and satellite systems matching telescopic observations down to startling details. One of simulation's greatest triumphs is revealing how randomness and inevitability intertwine in galaxy formation. Start two virtual universes with nearly identical conditions, and their galaxies will still diverge. Tiny fluctuations in initial gas density snowball into vastly different structures over billions of simulated years. Yet amidst this chaos, overarching patterns emerge. Dark matter always forms filamentary scaffolds first, gas pools at intersecting nodes, and mergers inevitably trigger starbursts. The Eagle simulations demonstrated this beautifully, showing how galaxies self-regulate their growth. Too many stars form, and supernova explosions blow away remaining gas. Too few, and gravity draws gas back in, reigniting star formation. It's a delicate dance that no telescope could decode from snapshots alone, but simulations make the rhythm visible. Some of the most enlightening moments come when simulations fail. Early models produced galaxies with bulges too large or disks too small, clues that physicists had underestimated key processes. Only by adding supermassive black hole feedback did newer simulations like FIRE to correctly replicate the mix of spirals and ellipticals we observe. These virtual universes act as stress tests for our theories, their flaws highlighting gaps in our understanding. When simulations of the Milky Way's formation couldn't explain its current satellite galaxy arrangement, astronomers realized our galaxy's merger history must have been far quieter than assumed, a revelation later confirmed by Gaia telescope data. The scale of these projects is mind-bending. The Millennium simulation used 10 billion particles to model a cube of universe 2 billion light-years wide, tracking cosmic evolution from just 300 million years after the Big Bang to today. Analyzing its data required machine learning algorithms to categorize galaxies by shape and color, tasks humans would need centuries to complete. Yet even these vast simulations simplify reality. They approximate gas physics with equations that can't capture every turbulent eddy, and model star formation with rules derived from observations rather than first principles. What makes simulations indispensable is their ability to isolate variables no telescope can filter out. Want to see how galaxies evolve without supernova feedback? Just turn it off, curious whether dark matter is warm or cold. Run both versions and compare the results to real galaxies. This virtual experimentation led to breakthroughs like understanding why dwarf galaxies are rarer than predicted. Gas heating from early stars suppressed their growth, and how the Milky Way's bar funneled gas to its core, revealed by tracking virtual particles in the Auriga simulations. The future of galactic simulations lies in ever greater resolution and physical fidelity. Projects like CAMELS now incorporate machine learning to refine their models, while exascale computers promise to simulate individual star formation within galaxy-scale volumes. As these virtual universes grow more intricate, they'll keep challenging our assumptions, revealing not just how galaxies form, but why they look the way they do, and what their diversity tells us about the invisible forces shaping our cosmos. For astronomers, they've become as essential as telescopes, digital oracles turning equations into galaxies, one particle at a time. Despite centuries of observation and decades of cutting-edge simulations, galaxies still guard profound secrets that defy our understanding. Among the most puzzling are ultra-diffuse galaxies, cosmic ghosts so faint they were nearly invisible to telescopes until recently. These enigmatic objects, like Dragonfly 44 in the Coma cluster, span sizes comparable to the Milky Way but contain just 1% of its stars, scattered so thinly their light barely registers. How something so massive yet so dim formed remains a mystery. Some theories suggest they're failed galaxies whose gas was stolen early by voracious neighbors, leaving them frozen in adolescence. Others propose they're normal galaxies whose dark matter halos mysteriously expanded, scattering stars into obscurity. Their very existence challenges textbook notions of how galaxies should look and evolve, proving the universe still has surprises up its sleeve. Equally baffling is the role of dark matter in galactic evolution. While we know this invisible substance outweighs normal matter 5-to-1, its exact influence on galaxy shapes and behaviors remains hotly debated. Take the bizarre case of NGC 1052DF2, a galaxy with almost no dark matter at all, a cosmic rule breaker that shouldn't exist under current models. If dark matter is the scaffolding for galaxy formation, how did this object build itself without it? Some speculate it was stripped away by a violent collision, while others wonder if our understanding of gravity itself needs revision. The debate grows even murkier with cuspy halo problems in simulations, where predicted dark matter densities in galactic centers don't match observations. Is this a flaw in our models or evidence of dark matter particles interacting in ways we haven't yet imagined? Then there's the puzzle of disk galaxies that defy aging. Spiral galaxies like NGC 3200 should have thickened into messy ellipticals after billions of years of stellar motions and mergers, yet they maintain pristine disks thinner than expected. What invisible mechanism keeps these structures so delicately balanced? Some point to dark matter halos acting as stabilizers, while others invoke mysterious magnetic fields or even undiscovered particles subtly influencing stellar orbits. Even more perplexing are blue nuggets, compact galaxies in the distant universe forming stars at impossible rates without blowing themselves apart. Their existence hints at regulatory processes we've yet to uncover, missing pieces in our galactic formation playbook. The mysteries multiply when we peer back to the universe's infancy. JWST discovery of massive, mature galaxies existing just 300 million years after the Big Bang has thrown cosmic timelines into chaos. These precocious giants, like Glass Z13, formed stars faster than physics should allow, as if they skipped multiple steps in galactic evolution. Were there seeds planted by exotic dark matter variations? Did they form through mechanisms lost to cosmic time? Every answer we uncover seems to reveal deeper questions, reminding us that galaxies aren't just puzzles to solve. They're conversations across billions of years, whispering secrets we're only beginning to decode. Every atom in your body, every breath you take, has a lineage stretching back to the heart of dying stars and the swirling chaos of young galaxies. The connection between galactic evolution and life isn't poetic coincidence, it's a chain of cause and effect written into the fabric of the universe. Consider carbon, the backbone of organic chemistry, forged in stellar furnaces scattered across space by supernovae, then incorporated into molecular clouds that birthed new stars and planets. Or oxygen, essential for respiration, created in massive stars and expelled in their violent deaths. These elements didn't just appear, they were meticulously crafted over billions of years through processes only possible in galaxies rich with stellar diversity and dynamic interactions. Spiral galaxies like the Milky Way offer particularly fertile ground for life's ingredients. Their orderly rotation allows gas to persist for eons, cycling through generations of stars that progressively enrich the interstellar medium with heavier elements. The Sun's position in our galaxy's habitable zone, far enough from the crowded, radiation-bathed core yet close enough to benefit from earlier stellar generations, wasn't random chance. It resulted from galactic processes that distributed metals outward over time, creating a Goldilocks region where rocky planets could form with the right mix of elements for complexity. Even Earth's protective magnetic field owes its existence to heavy elements like iron and nickel that sank to our planet's core, materials only available because ancient stars died in galaxies that had time to mature. But the relationship between galaxies and life runs deeper than raw materials. Galactic mergers, though destructive on cosmic scales, may be essential for life's long-term prospects. When the Milky Way collided with the Gaia Enceladus galaxy 10 billion years ago, the influx of fresh gas likely reignited star formation in our galaxy, including the birth of our Sun. Without that violent encounter, the specific combination of elements and orbital stability that made Earth possible might never have arisen. Similarly, the Milky Way's barred structure, a product of gravitational instability, acts like a conveyor belt, funneling gas inward to sustain star formation rather than letting it stagnate. Life, it seems, thrives in galaxies that balance chaos and order, where turbulence stirs the pot just enough to keep the cosmic chemistry lab running. The timing of galactic evolution also plays a crucial role. Planets forming in the universe's first galaxies faced harsh conditions, intense radiation from early quasars, frequent supernovae, and a scarcity of heavier elements needed for complex chemistry. Only after several generations of stars had enriched the cosmos with carbon, nitrogen, and oxygen could terrestrial planets like Earth emerge. Even now, as galaxies age and star formation slows, the window for life may gradually close. Elliptical galaxies, having burned through their gas in frenzied starbursts, become celestial retirement homes with little material left to birth new planets. The universe's lifespan, its youth too chaotic, its old age too depleted, may have a sweet spot for life, and we're fortunate to exist right in the middle of it. Perhaps most astonishing is how galactic-scale events leave fingerprints on life's evolutionary path. Geologic evidence suggests that nearby supernova may have triggered mass extinctions by bathing Earth in radiation, while the solar system's periodic journeys through the Milky Way's spiral arms could expose us to increased cosmic rays, potentially influencing mutation rates. Even dark matter, though invisible, might shape life's story. Some theories propose it could heat planetary cores through subtle interactions, prolonging geologic activity that stabilizes climates. From the tiniest microbe to the tallest redwood, life doesn't merely inhabit a galaxy. It's woven into its ongoing narrative, shaped by forces both vast and intimate. This cosmic perspective transforms how we see our place in the universe. The same processes that sculpt spiral arms and light up quasars also forge the calcium in our bones and the iron in our blood. When we study distant galaxies, we're not just exploring abstract realms, we're uncovering chapters of our own origin story, written in starlight and atomic bonds. The universe could have taken countless paths, yet the one it followed led to galaxies capable of wondering about themselves. A profound feedback loop where matter organizes into forms complex enough to contemplate its own existence. In this grand tapestry, every supernova, every galactic collision, every swirling disk of gas was a prerequisite for the moment life could look up and ask, "How did I get here?" From the faintest wisps of hydrogen in the cosmic dark to the dazzling spiral arms we see today, galaxies transform in ways that still leave us in awe. What begins as an almost imperceptible ripple in the fabric of space, a cloud of gas so diffuse it could drift unnoticed, slowly gathers under gravity's patient pull. Over billions of years, chaos gives way to structure. Collapsing gas ignites the first stars, dark matter weaves an invisible scaffold, and mergers sculpt elliptical giants or delicate spirals. Yet this isn't some ancient, finished process. It's happening right now, in our own Milky Way and in galaxies so distant their light is just reaching us. Every supernova explosion, every galactic collision, every new star flickering to life adds another brushstroke to an ever-changing cosmic portrait. Take a moment to consider the scale of this evolution. The same forces that shaped the Andromeda Galaxy's swirling arms also carved the delicate filaments of gas in the Orion Nebula, where new stars are being born even as we speak. The oxygen we breathe, the silicon in Earth's crust, the gold in our jewelry, all were forged in the hearts of long-dead stars, scattered across space by galactic forces we're only beginning to understand. This isn't just history, it's an ongoing story where we're both witnesses and participants. Our very existence is tied to these grand processes, a reminder that galaxies aren't just distant lights in the sky, but the architects of everything we know. What's thrilling is how much remains undiscovered. With every technological leap from Galileo's first telescope to JWST infrared gaze, we peel back another layer of the mystery. Why do some galaxies defy our expectations by forming too fast or shining too bright? What unseen laws govern dark matter's subtle dance? Each answer sparks new questions, keeping the wonder alive. That's the true beauty of astronomy. It's a never-ending invitation to look deeper, think bigger, and stay curious. If this journey from gas clouds to galactic majesty has sparked your imagination, you're not alone. The universe has a way of captivating anyone who takes the time to look. So keep exploring, whether through a backyard telescope, stunning space images, or videos like this one. And if you enjoyed this cosmic ride, don't forget to like and subscribe for more deep dives into the universe's greatest wonders. Drop a comment below sharing which galactic mystery fascinates you most. After all, the next great discovery could start with a simple question, and who knows, maybe yours will be the one that changes how we see the cosmos. Until next time, keep looking up. The universe has endless stories.